Welcome to lesson 3 from chapter 3, functions. This is from year 2 pure mathematics. Today we're going to take a look at the idea of a composite function. Okay, so we're going to learn about what a composite function is and how to work with them. So we'll get started straight away. There's not many new keywords in this section, so please pause the video and have a go at the 4 warm questions. Okay, and let's now have a look at the solutions. So question 1, we are asked to make some simple substitutions into our two functions f and g. Note that x can be any real number. Okay, so we have a domain defined for both f and g. So f of 2, we simply have to, this is for part A, we simply have to replace x in our function with the number 2. That's the instruction. So you can see, of course, that in the function itself, we have an x here and we have an x here. So those are going to be replaced by 2 when we make that substitution. Essentially, that's what substitution is. Okay, so 2 multiplied by, and I'll substitute, I'll make my substitution in red, 2 plus 1. So that's going to give us 5 in total. Okay. Now we have a substitution in the function g. So again, in the function g, it's a function of x. So I need to replace x here with whatever I'm substituting x for. So in this case, it's 5. So I'm going to replace x with 5 all the way across. So g of 5 is simply going to be 5 squared. Okay, and you'll have seen this before. So 5 squared, which is of course 25. Okay, now we're going to carry out g of 2. So g of 2, we replace x squared with 2 squared. So 2 squared, just be careful, of course, to substitute into the correct function, which is 4. And f of 4, so we go back to the function f and we're replacing x with 4 this time. So it's now going to be 2 multiplied by 4. And we're going to add 1. So that's going to give us 9. Okay, so this is something you need to be proficient at when we're carrying out this lesson today. Moving on to question 2, we have more algebra. We have to expand and simplify these expressions. And there's an interesting theme going on with this, which you'll see more of later. So we have to expand and simplify 3 multiplied by 3x subtract 2, all subtract 2. So looks like some kind of nested function there, doesn't it? 3x subtract 2 inside 3x subtract 2. So let's do that. So expand the bracket first. So 3 multiplied by 3x subtract 2 is going to give me 9x subtract 6. So that's expanding the bracket, which I've done there. Okay, and then we have to subtract 2 on the outside. Okay, and then the simplifying is, of course, collecting the like terms. So we collect the 9x together. There's no other x's to collect together. Subtract 6 and then subtract 2 will, of course, give me negative 8. Okay, moving on to the next one, we have to square 3x subtract 2 this time. So square all that. So that's going to be 9x squared subtract 12x plus 4. Okay, and this time we're going to subtract 1. Okay, so again, if you're not too happy with expanding just in one step like that, remember, just write them out like this. Okay, you don't have to do it in one step if you don't want to, and you won't be penalized for doing it in one step either. Okay, so this is all equal to, so I'll just have to partition that off now. 9x squared subtract 12x, and then we have to subtract 1 from 4, which is of course going to give us plus 3. Okay, and for the last one, we have to first multiply the x squared subtract 1 by the 3. This is, of course, using our BODMAS. So that's going to be 3x squared, subtract 3, and then I've got to subtract 2 on the outside of the bracket. All right, so this is going to give us 3x squared, subtract 5. Okay, so some simple expanding and simplifying that you've met many times before. So let's move on to question 3. So now we fast forward into some more recent topics. So we have here a reciprocal function, and I just want to stress that if you don't like this function notation, it is no different from writing f of x in the following way. So please don't let that put you off. So it's 1 over x plus 1, and the domain specified here is x is greater than 0. So if you prefer, rewrite the function in the notation you're more familiar with. Now then, we have to deduce the range. So we have the domain given to us, so we have to be mindful of this while we're trying to deduce the range. And a good way to do this would be to do a sketch, okay? Now, there's a couple of things you need to be thinking about while you're doing your sketch. Obviously, this is a reciprocal function, so we need to be thinking about asymptotes. All right, so you don't have to write this stuff down. This is just thinking aloud, really. These are the things you should be thinking of. So horizontal and vertical. And we'll test for those in a second. And we also need to, once we've got any potential asymptotes in place, we need to think about any possible x and y intercepts. So the reason why that's important is knowing where the intercepts are will fix your curve in place, so you know you've got an accurate sketch. All right, so we'll look at the asymptotes first. Now, the simplest one to find first is a vertical asymptote, and we'll get a vertical asymptote if we imagine that the denominator of this reciprocal function is 0, because that's what we're not allowed to substitute in. So if we imagine, just for the sake of argument, if we could put that equal to 0, I know we're not allowed to, but if you set it equal to 0, it gives us an equation, doesn't it? So if we solve the equation x plus 1 equals 0, we effectively get x is equal to -1. Now this is your vertical asymptote, okay? Now you'll be like thinking, but you're not allowed to put -1 in, that's not in our domain. I'm aware of this. We're just going to treat the whole of the real line as the domain initially, and then we will restrict the domain later when we're trying to deduce the range. So we've got a vertical asymptote. We also need to think of horizontal asymptotes. Now, the way to do that, as we've discussed in class quite a lot, is to imagine what happens as the x value here gets really big, okay? Both in the positive and negative direction. Now, if you put a really big number in for x, so we're at numbers way down in the positive real line, you'll notice that we'll be doing 1 over an incredibly large number, which is effectively going to be 0. It's the same in the negative direction. If you put a really huge negative number into this function, you'll get approximately 0, but it'll be on the slightly negative side. So it seems that we're approaching 0 as x gets very big. The fact that we're adding 1 is irrelevant when you're talking about enormous numbers. So we also have, so this is the vertical asymptote. Okay, so we'll just write down what we've just discussed for the horizontal asymptote. So as x gets very big, so as x approaches infinity, f of x approaches 0. Okay, so that means, I'll just do this in a different color. So we have y equals 0. This would be the horizontal asymptote. All right, so we've got that. Now I think we'll put the sketch together now. So just draw some axes. So we've got a vertical asymptote at x equals -1 and horizontal asymptote on the x-axis effectively. So we'll put those in. Label your axes. This is not redundant work, okay? This is the way to work out these ranges. Now, let's put in a vertical line for the asymptote at x equals -1. And it's also because I'd like you to practice as much as possible sketching these curves. Okay, so x equals -1. Okay, there we go. And we have a horizontal asymptote along the x-axis. So I'll just overlay that. All right. So we've got y equals 0 here. Now then, we also have to think about y and x intercepts. Now, the y-intercept, of course, we just have to sub in x equals 0. Okay, now if we put x equals 0 into this function, we get y equals 1. So there's the y-intercept. So we know we've got a y-intercept here at 1. Okay, and x-intercepts, well, there aren't any because that's where the asymptote is. So we now have the curve fixed in place, and because it's reciprocal, it's going to be in the opposite quadrants. So we've got a curve coming down here like this. I'll try and draw this accurately if I can. Okay, and we've got a curve this way. So this would be the graph of y is equal to 1 over x plus 1. So we've spent a bit of time putting that together. Now then, what we have to consider now is what happens when we restrict our domain. So if we go back to our original question, the domain here is just x is greater than 0. So the only x values I'm allowed to put in are along this part of the line, okay, not including the origin. And our job now is to deduce what happens on the y-axis. So what are the corresponding y values I can get out of this? So ignoring the whole left-hand side of this sketch, you'll notice that the y values that we get out of it, just for this branch, which I'll just redraw, okay, just for this branch here, so that's the only bit I'm interested in, the only y values are going to go between 0 and 1, which you can't quite see, it's been hidden by my curve, okay? Now 0 is not included because that's where the asymptote is, but 1 is included because it is defined at that point when x is 0. Okay, there is a particular point on the curve which we call 1, which is included. Okay, so let's write down the range. In fact, I've just said that wrong, haven't I? I'm talking nonsense. 0 is not included. I apologize. So the range is going to be between 0 and 1, not inclusive. Okay, 1 is not allowed because you're not allowed to sub 0 in. Oh, I hope that makes sense. Okay, so there's the range. So all values between 0 and 1, but 0 is not defined and 1 is also not defined. Now then, let's move on to question 4. So we have to simplify this rather ugly looking reciprocal expression. Right, so just take a look at it. If you haven't had a go at this already, maybe just pause the video, just have another go, see if you can figure out a way, look at some commonalities, see if you can figure out a way of maybe making this look a little bit less aesthetically unpleasing by removing the fractions within the fractions. All right, now what we need to do here is, you'll notice, if you haven't noticed already, we have x subtract 4 as our denominator of the fractions within the fractions. So it's the same fractions essentially, just with +1 and -1, okay, in the numerator and denominator respectively. So a good idea is to clear this, or to clear these fractions. Now, what we need to do then is, if we multiply the entire numerator by x subtract 4 by the whole thing, okay, now we know that that will clear the denominator of the fraction on the left in that numerator. And we're allowed to do that as long as we do the same thing to the denominator. And this is actually really good news, because this will also clear the denominator in the denominator, if you see what I mean. So the denominator of the fraction in the denominator will also be cleared. Okay, so we're going to perform the same multiplication top and bottom, which is what you have to do with fractions if you want to maintain equivalence, of course. Right, so let's see what happens when we do that. So initially, we're going to clear the denominator, so we're going to get x plus 2. Okay, now that the denominator's gone, but we have to multiply the 1 in that numerator by x subtract 4. So I'm forced to multiply this by x subtract 4, but at least I've got rid of that denominator. Okay, now this is all going to be over. Now let's do the denominator. So it's going to be x plus 2. Again, the denominator is going to clear. And this time I'm going to subtract 1 multiplied by x subtract 4. Okay. Now it looks like a lot's changed about our fraction. It hasn't really. It's just that these have cleared because I'm multiplying by x subtract 4, and these two terms have been multiplied by x subtract 4. And already it looks a lot better. So now we just collect like terms. I'll expand first of all. So we're going to have x plus 2, and then we just have plus x subtract 4, just multiplying everything by 1 there. I'm just doing another step here because the denominator, we have to be a bit careful here. So we now have x plus 2 in the denominator, and then we have -1 multiplying all that. So -1 multiplying everything inside the bracket. So that, of course, is going to give us negative x plus 4. All right, now let's tidy everything up. We should be there. So in the numerator, we've got 2x. So x plus x is, of course, 2x. So get that in. And we have plus 2 subtract 4, so that's -2, all over. Now the x's will cancel, as you can see, because we have a positive and a negative x here and here. And then we have 2 plus 4, which is, of course, 6. Okay, so that's all over 6. And you'll also notice we can cancel 2's everywhere. So this is going to be 2 multiplied by x subtract 1 over 6. We'll cancel those down. So all that rather nasty looking fraction is just x subtract 1 over 3. Okay, and if you want to test this, just try some values, put some x values in and see if they are in fact the same. Okay, so that concludes the warm-up. So let's first have a look at the basic concept behind a composite function, okay? A composite function is exactly what it says it is. It's one function combined with another, a composition. So if we look, first of all, on the left-hand side of this diagram, this part here, this represents the domain, but it represents the domain of G, okay? Initially, we'll talk about FG in a moment, which is the arrow at the bottom. So the domain of G, which I'll just label here. So if we are taking the function G, we take an object from the domain of G, which is an X value, and it gets mapped to an image, which we call the range, of course, as you know now. So this is the set of the image of all X values, which we call the range. So again, I'll just write down what that is. But this is the specific range. So this is the range of G, okay? We could also say that our initial domain here, this is the domain of G as well, okay? It's where all the elements from the objects are taken, so they're taken from that domain. Now what happens is, so we now, that's the typical function diagram, isn't it? So you take your domain, elements from your domain, you map them to elements in your range. But when we bring another function into it, what happens is that we now take elements from the range of G and we map them using a different function, or it could be the same function, it doesn't matter. So we take all the elements from the range of G and we take the function f and then we map it to a new set, okay, over here. Okay, now this would be the range of f. Over here. And what's interesting is that the range of G also doubles as the domain of f. Okay, so it's like you're putting two function diagrams combined together, which is what a composition is, isn't it? Now, so there's two processes going on here. So x is mapped to G of x, and then G of x in turn is mapped to what we call fg of x. Right, so there's two processes, and I can just highlight the process. So x here is mapped all the way to G of x here, which is then mapped via f to fg of x on the right-hand side. So how does this play out algebraically? Because we can see clearly that there's two domains here, and we've got two ranges. Well, what we're saying is that if we take this function G of x, which I'll just do here in green. Okay. That means that we've taken an x value. This is all that means. We've taken an x value and we've mapped it to some value G of x. And then once we've got that, the result is staring at us. We put that into, so I make this now an element of the function f, so an element of the domain of f. So we put the G function inside the f function, okay, because G is our domain and we map our domains using our function. And this means that we now take our G and we map it to f, okay, but it's not f of x, it's f of G of x, because of the domain we've chosen. So just squeeze that on there. Not quite. Let me try that again. Just undo that. Okay. Just want that. It's quite an important piece of the diagram, so I just wanted to fit that on. So this goes to f of G of x. Right. And you've been doing an exercise which will get you used to this when you did the warm-up. So this is how it plays out. So you can see that putting these two ideas together, we get a function which we can effectively just call fg of x, and we write it like that. Okay. You might also see it written as f with a circle, so it looks like fog, FOG of x, like that as well. That the circle is just mathematical terminology for composition. Okay, so that just means composition. You don't need to worry too much about that. You might see it though if you're googling this stuff, or you're trying to find some extra examples. You might see that it just means the same thing. Okay, so that's effectively what a composition is. And going back to the diagram, this FG of x, which I've just mentioned, you can describe it as one single function. Okay, so f with g composed inside it. Okay, taking your x values from here, putting them into g, and then putting them into f, and then taking them directly to the image of f, which we now call fg. So I could also relabel my domain and range as follows. So I could say, well, this is the domain of fg. Okay, and then skipping the middle, this is the range of fg. Okay, I hope that makes sense. So let's try this idea out. We'll have a look at some examples using some simple functions. So we'll do some simple compositions, and then hopefully you can try some using it through an exercise. So first up, we're going to have a look at two functions, h and k, that I've defined, as you can see. So h of x here, it's 3x subtract 2, which is just a simple linear equation, linear function, and a quadratic function here. Okay, the domain is all real numbers, right? So that's just something to take note of, and we have to find the functions. Now, hk, first thing to do, ladies and gentlemen, is to state clearly what we are intending to do. So just as a reminder, in this instance, I can write this hk as follows. So this is for part A. So I could write hk of x. Now what that means is that I'm applying the h function after I've applied the kx function, okay, the k function. So I'm putting the k function inside the f function, and this is where you get the misconceptions, because the h comes first, if you notice, but it's the k function that you actually do initially, and I'll just remind you of that. So what's actually happening is we take the x value from our domain, our real numbers, we apply the h function to them. Sorry, no, I apologize. We apply the k function to them. So my x values from my real number line are mapped to k of x, and the range will also be all real numbers. And then that gets mapped to h of k of x. So in fact, I'll do that in a different color. So that's going to be h of k of x, like that. So what is happening is that you apply k first. In fact, it'll probably be better if I put it here. So we're applying k here, and then here we're applying h to our x values. Okay, so apply k first, then h. So how does this look when we're doing this algebraically? Well, what we need to do is, if you notice, we've got the k of x there. I know that the k of x is simply x squared subtract 1, which you can see here. Okay, so my input to h should be x squared subtract 1. So let's open the bracket. So instead of putting in x, I'm putting in x squared subtract 1. Like that. So that's now my input into my h function. Now then, how does that look? Well, this means that if my input into h is x squared subtract 1, wherever I see an x in my function, so i.e. here and here in my h function, I have to replace it with x squared subtract 1. So let's do that. So this is going to be 3. Let's try that again. This is going to be 3. And then we're going to multiply that by, sorry, I'm just having a bit of trouble here. Multiply that by x squared subtract 1. Close that bracket. And then what do we have to do next? Well, we have to subtract 2. Okay, so we subtract 2. So you can see I've put the h function inside the, I've said it wrong again. I've put the k function inside the h function. Okay, the k goes first, even though it's the second function if you're reading from left to right. So that goes first and then that goes second. Okay, I'll just make a reminder of that. Now all we have to do is expand and simplify. So this is going to be 3x squared, subtract 3, and then of course you've just got to subtract the 2 off the end, which is why we practiced this earlier. So this is going to be 3x squared, subtract 5. All right, so that is the function hk of x. Okie dokie. Let's move on to part B. Now we do it the other way around. So we're now going to put the, I can do this here in fact. So now I've explained it a bit more. We put the h function into the k function. So if we do kh of x, what this means is that we take the k function, but our input is going to be the h function. Okay. Like that. What does that look like? Well, it means that wherever I see an x in my k function, i.e. here and here, I have to replace it with whatever h of x is. So whatever this is. And it's a good idea just to write down what h of x is. That's 3x subtract 2. So 3x subtract 2, like that. Okay, and we plug all that in. So we put 3x subtract 2 into k. We're going to get 3x subtract 2 all squared. And then we simply subtract 1 on the end. Like that. Okay. And we did this earlier, didn't we? So once again, you can use your work from previously, but I'll just write it out. So it's going to be 9x squared, subtract 12x plus 4, and then subtract the 1, which simply gives us this is our final answer. So this is going to be 9x squared, subtract 12x plus 3. Okay, and that's kh of x. Now let's move on to C. Now, what I recommend now is, now you've seen a couple of these, by all means, just pause the video and do these yourself and just check that you agree with what I get. Or if you're not sure, just listen. Now for part C, you've got HH. So you can do this. You can compose a function with itself if you like to. You sometimes see this written as h squared of x as well, because it's h composed with h. So let's just write out what's actually going on. So we know h of x simply means I'm composing h with itself. So I'm putting h of x into h, like that. All right, which essentially means that my input, which is this here, my input here is going to be the h function, which is all of the stuff over there. Okay, so I'm replacing all that with 3x subtract 2. All right. Now, again, we saw this earlier in warm-up question 2. We now put the 3x subtract 2 into that. So that means I'm going to have 3 lots of, and put the 3x subtract 2 in, like so. And then I've also got to subtract the 2. So again, we expand and simplify. So this is going to be 9x subtract 6 subtract 2, which equals 9x subtract 8. And that's h of x, or h squared of x. Now, moving on to part D, we're going to use the result from part A, where we found hk of x. But we also have an alternative approach. So I've just cleared the screen just to give us a bit more space here. Now, we're asked to find in part D hk of 3. And there's an important lesson to be learned here in terms of time management and when you're doing exams. Because if you find a composition of the functions h and k and you don't already have it, it can take up a lot of your time. And what I'm going to show you is you can use the composition hk, which we've got here, but if you're not already asked to do that, it can be quicker just to substitute in some values. So I'm going to show you what I mean. So for part D, one way of answering the question, of course, is simply to evaluate hk of 3 using what we've found from part A. So therefore, if I do hk of 3, substituting in the 3, then what we get is I just replace x in my function that I found from part A. So in other words, x here and x here, I place those with 3. So we get 3 multiplied by 3 squared. So that's 3 squared. Subtract 5, which is going to equal 27. It's 3 lots of 9. Subtract 5, which of course gives us the answer 22. So that would be one way to evaluate it. So evaluate means find the value of, essentially. So you've got a numerical answer. Now, alternative, and this is preferable in exams, is to do the following. So let's assume we don't have the prior knowledge of finding hk of x from a previous part of the question. So what we need to do is, when we're doing hk of 3, what we first need to do is find k of 3 first. All right. Okay, so if we do k of 3, remember, when you're composing functions, it's, in fact, I should write that down. It's k of 3 evaluated, and then that is put inside the function h. So it's h of k of 3 like that. So k of 3 is your input. So if we do k of 3, let's see what we get. And we can do this quickly because you'll be given the functions in the question. So k of 3 is, of course, going to be 3 squared subtract 1. So we just have to square 3 squared subtract 1. And I'm just obviously referring to this part here, k of x, like that. That's going to give us 9 subtract 1, which is, of course, 8. So that's k of 3 evaluated. So what we now know is, now we've evaluated that, the k of 3 evaluated means that what I have to do now is to find out what h of k of 3 is, which is, of course, 8. So I can replace the k of 3 with 8, which I've just discovered, and we put that into the function h. So I take the answer that I've just got, which is right here, and this goes into h. So let's just draw an arrow. So that's really important. Take that value, whatever it is, and we go to the next step. So h of 8 is simply going to be, let's have a look, what's the h function? 3 multiplied by 8, and then subtract 2. Okay, so this is going to be 24, subtract 2, which is, of course, 22. So we just verified the previous result here. We've got the same answers, of course, we've got, which you'd expect if this whole thing works. But in terms of the exam, although the right-hand side looks like it takes longer, it doesn't, because I've omitted all the working out we did for part A. So just please be mindful of that. The HK of 3, that type of question, is your typical part A functions question on exams. And it is much better just to substitute the value in to the first function, the K function, and then in whatever you get as your answer, that then goes into the H function. So for worked example 2, we're just going to take a bit of a sidestep here, and we're going to go and look at piecewise functions as defined when we were talking about domain and range. So this function f of x, it has two branches. It has this quadratic branch here defined for all x strictly less than 2, and then it switches to a linear graph when x is greater than or equal to 2. And our first job, of course, is to sketch it. So the reason why we're taking this sidestep is because if you look at part B, we are asked to make or evaluate a composition of functions by substituting 0 into f. And what I found was in the past, several candidates were getting this wrong on a technicality, really, but it's really worth just going through the concept as clearly as and as meticulously as possible, just so that we don't make that mistake. All right, and it involves a deep understanding of composition and also of how functions behave. So this is why I just want to spend a bit of time on this example before we move on to extend the worked examples that we've looked at already. Right. So let's have a look at the quadratic part of this. Let's see if we can find some key characteristics. Well, looking at the way it's written in completed squared form. So I can see straight away from the -2 here and the 1 here that we have a minimum. Also, it's a smiley quadratic. So there's a minimum at the point 2, 1. Okay. But I'm going to say with caution that this minimum point is not actually a feature of the function, because 2 is not defined. X is strictly less than 2. So although 2, 1 would be on this quadratic if it was defined for a broader range of x values, so something like all real numbers, we just have to say that it's not a part of the function. Okay, I'll just put it in sort of simple language. So not a part of the function. Now, what else can we deduce from this? Well, if we expand the brackets, which I'll do now. So just going down here, just got a bit of room. I can expand this. I get x squared subtract 4x, and that would be +4, and then add 1, that would be +5. So that is now telling me, once I've expanded that, we have a look, and you know how to interpret it. We have a y-intercept at +5, so that's good as well. So we'll just write that down. (0.5). Now that is on the function because 0 is obviously strictly less than 2. So I think we've got enough there to lock everything in position. We've got the y-intercept and we know where the minimum point is going to be. The second part of the graph is the straight line part. So it's the 3x subtract 5. So they're relatively easy to sketch, of course, but we need to be very careful because we need to know how it relates to the previous branch. So it would be a good idea to find out where this graph is located when x is equal to 2, because that's where the domain starts, where this straight line graph takes over. So if we just sub in x equals 2 into our straight line, so when x is equal to 2, we get 3 multiplied by 2, that's it, obviously. So subbing the 2 in, and then subtract 5, we get 6. Okay, so that tells me that the point, sorry, that's not right. 6 subtract 5, I apologize. 6 subtract 5, which is of course 1. So that tells me that the point 2, 1 is a part of the function. All right, so I've seemed to have contradicted myself here, because I've already stated that 2, 1 is not a part of the function. But when I'm talking about the point 2, 1, I mean that it is a feature. So this 2, 1 here is a feature of this part of the function, okay? But it is not a feature of this part, okay, the quadratic. Okay, so 2, 1 is on the straight line branch, but not on the quadratic branch. Okay, I'll make that clear. Right, so now we're in a position to draw this. So we're going to draw some axes. So let's put those down there like that. So you can draw this in the space provided. Put the horizontal x-axis on here like that. Don't forget to label them, of course. So this is x, the origin, and y. And the key point here, of course, is the point x equals 2. So I'm going to indicate that on here. So x equals 2, so I'll put that there. And we know that that's where the minimum point of the quadratic would be. So it'd be somewhere around there, perhaps. And we also have that y-intercept at 5. So I'm just going to put a little cross there just to show where that point, that minimum point would be. But just bearing in mind, of course, that this is not part of the function of the quadratic part. It is part of the straight line branch. So let's put this curve in now. So it's going to go something like this. Okay, that y-intercept there is going to be the point 5, as we found earlier. And that's the quadratic branch done. Now then, the graph behaves like a straight line graph for the rest of this. So let's use a different color. So this point here, I'm going to do a solid circle here. That is part of 3x subtract 5. And 3x subtract 5 is just a straight line, which would normally cut at -5. And it's got a gradient of 3. So it's going to probably do something quite steep like that. Okay, so we have our 2 branches. So I'll just label those. So this would be the graph y is equal to 3x subtract 5, but just for x greater than or equal to 2. And this part is y is equal to x subtract 2 all squared plus 1, but only for x strictly less than 2. Okay, so I hope that makes sense. So we've got our sketch. So that's part A done. We can just label the box here as part A. Okay, and of course the whole thing is just y equals f of x. Right, so for part B, this is where we're going to use our compositions of functions. So we can use the lined section here. So for part B, we have to find f of 0. Now, to do that, of course, we've just seen that this is basically telling us to put f of 0 into the function f itself. Okay, so f of 0 into f. So the input of f is f of 0. So what we need to do is figure out what f of 0 actually is first. And you'll see why we've got to be careful right now. So if I figure out what f of 0 is, so therefore f, let's rewrite that. So f of 0, putting 0 in. Now we have to be careful which part of the domain we're working in. So 0, of course, you can see is going to be in this part of the graph. I'm just highlighting with an asterisk. And on the graph, of course, 0 is here. So it's the quadratic part like that. So we can see it's going to be 5 because it's the y-intercept, but we'll just evaluate it anyway. So this is going to be 0, subtract 2, all squared plus 1, okay, which is obviously just going to be 4 plus 1, which is 5, as predicted. So that's f of 0. So we take our f of 0, which is 5, and we have to substitute that back into the function. Okay, so this needs to go back into our function f. So I'm going to take that, I'm going to go to a new line, and we're going to sub it in. So now we have to find f of 5. And you may have spotted why we have to be careful here. So f of 5. Right, now this is the problem. 5 is now in the other branch, okay? It'd be somewhere over here, which is where the graph is now a straight line. So we can't use the same quadratic component of the graph, the same quadratic branch, because that would be wrong. The function is not defined for an input of 5, okay? As a quadratic, it's a straight line. So we now put the 5 into the straight line part of the graph. And that's the bit you've got to be careful about. So this would be 3 multiplied by 5, okay, and then subtract 5. Because if you do this too quickly or without thinking, you'll substitute the 5 back into the quadratic, as many people do on these exam questions, which is going to be 15 subtract 5, which is going to give us 10. So that's the answer for part B, okay? And the reason why I've spent so much time on this example already. So all we have to do now is find the range of values of x for which f of x is greater than 7. So this is going back to what we did when we're looking at domain and range. A good idea, of course, is just to find out where 7 is on the graph. So I'm going to put a straight line on here. Let's do a green one. No, we've already got green, haven't we? Let's do a purple line. So 7 will be somewhere across here. So let me just, on the wrong setting. So let's go across. So it'll be something like that. So let's call that y equals 7. Okay, and we're interested where this graph, so there and there, so those are the points of intersection, but we're interested in where the graph is greater than 7. So i.e. all this part, which values of x does this happen? So what we've got to do is we've got to solve some inequalities. So as you can see, to answer this question, we need to solve 2 inequalities. We need to solve when the quadratic part, so when x subtract 2 squared plus 1 is greater than 7. We need to solve that. And we also need to solve 3x subtract 5 is greater than 7. And all the time, we need to be mindful of this sketch. Okay? And what I probably better do is just remove this so it doesn't look misleading. Okay. So we need to find out what these values are. So the first one, let's do the quadratic. This looks more tricky. So if I subtract 1 from both sides, we're going to have x subtract 2 all squared has to be greater than 6. and we take the square roots. Now, of course, we can take a positive and a negative square root here. We do need to be careful. In fact, what we should probably do, I'm going to expand the bracket, subtract 4x plus 4 is greater than 6, and I'm going to form a quadratic inequality instead. So we've got x squared, subtract 4x, subtract 2 is greater than 0. Right. So we have to solve this inequality. The quadratic has to be strictly greater than 0. Okay, now if you plug all this into your class whiz, so we'll just write down what A, B, and C are. So A would equal 1, B would equal -4, and C would equal -2. You get two solutions, of course, so I'll just write down what the class whiz tells us. So from all this, we get first solution. So x is going to be 2 plus root 6. You can just verify this on your class whiz. Okay, these are for the roots, or x is equal to 2 subtract root 6. So those are the roots. Now, if we just check this on a graph, remember we want values that are greater than 7. We just need to do a little sketch of the quadratic graph. So let's do that. So we've got the x-axis here, like that. It's a smiley graph, of course. So it's going to go like this. And we're going to have the two roots. So we're going to have 2 subtract root 6 would be the lesser one. Okay, which would actually be a negative number, and 2 plus root 6 would be over here, like so. And then you just inspect this and think, okay, where is this graph positive? Okay, so it's the positive branches, has to be greater than 0. So obviously, for our solutions to this, x would have to be, undo that, so x would have to be strictly less than 2 subtract root 6, or x would have to be strictly greater than 2 plus root 6 in order to satisfy this inequality. Now, that is just solving the inequality blind, okay? We've not really referred to our actual function in doing this. Now, if you look at the graph, it's only for x values that are less than 2, strictly less than 2, where this graph is defined. Now, if you look at our solutions here, we have one solution which is greater than 2. Okay, it's in fact root 6 greater than 2, which is here. Now, that means that that solution cannot be valid because it's outside of the domain. So this cannot be a solution. And you can also tell from the graph that the intersection point that we're interested in here is, if I've sketched this correctly, is going to be a less than 0. Okay, it's going to coincide with an x value somewhere around here, which is less than 0. So the only possible answer from this quadratic that we can possibly use is this one. So this must be the correct answer. And I'm going to highlight that and make a big fuss about it because that's a really important distinction. So this is the root that we need. Okay, and all that was just done from the class whiz. So just to remind you, I used a class whiz here for this. I just didn't want to put it on the screen because it's already quite a busy looking screen, isn't it? Okay, so I hope that's clear. So we've got one solution. We've got one solution already, and that's the most complicated one. So we now know that that point there would be the point 2 subtract root 6. Now then, what we haven't done yet is we haven't solved this inequality here, but this is much more simple than the previous part where we had to solve a quadratic inequality. So what we can do for this is just rearrange. So we get 3x is greater than 12. Okay, so just adding 5 to both sides. and then divide by 4. So x is going to be divide by 3. So x is greater than 4. And that is the second solution. Okay, there we go. And I'll put that in a red blob as well. So there's our other solution. Okay, so that's this point here. So this would be the point at the point 4. And we've solved the inequality. So next up, there is an activity for you to do. The answers are on the screen, and what you have to do is find the compositions of functions. I've actually given you all the solutions, so they're all pre-composed, if you like. So this is what kg of x is equal to. It's a quadratic. But what you have to do is just verify that. So if you compose g and k as specified here, do you in fact get the answer x squared plus 6x plus 6? So you can, it's self-checking, and I would like you to spend a bit of time doing that. There are 6 of them for you to try, just to practice your skills at compositions of functions and manipulation. So once you've done that, we're going to have a look at worked example 3. So I'm just going to scroll down. So this is the next thing we're going to be covering. It's the last worked example, and there's a few key points here I'd like you to be aware of. So what we're doing here is we're going to compose 2 functions, p and q. And p is a logarithmic function, q is an exponential function. And once again, if you're not comfortable with the notation, you're more than welcome just to rewrite p as follows. So it's p of x is equal to the natural log of x subtract 3. And you can see the domain here. X is strictly greater than 3 because you cannot take the log of a negative number and get a real value. Okay, there is an asymptote. X is equal to 3. All right, and if you also want to rewrite q, so we'll do that as well. So q of x is going to equal e to the power 2x. Add 1 to that, and that's defined for all real numbers. So there's no restrictions on the domain there for an exponential function. You can find the exponent of all positive, negative numbers, including 0. So we have to find a composition, and we have to state the range. So this is where we're going to bring in some of the work on logarithms and exponentials. So let's go through it carefully. So QP. So QP of x. What does that mean? Well, it means we take the function q, and as our input, we're going to put p of x in. So wherever we see an x in our function q, so just going back to that, wherever we see an x, so i.e. here and here, we're going to replace that with whatever the function p is, as stipulated there. So let's do that. So this is going to be equal to, now the q function is e to the power, now it's 2 lots of, now I've got to replace the x with p of x. So my x is going to be replaced by this is this function. So I'm going to put that in there. So this is going to be the natural log of x subtract 3, close the bracket. So this is looking complicated already. And then I have to add 1. Okay, so that's the composition. And there's nothing wrong with that, except it's hard to sort of deduce anything from it. But there's something interesting going on here. Let's just do a little bit of a recall or recap. Now, if we look at exponentials and logs, we know that they are inverse functions, or at least we should know. And when you compose inverse functions, we get the following properties. So if I take the function e to the x, and if I compose that with the natural log of x, because they are inverse functions, they cancel each other out. So you're just going to get the x value back, whatever it is. So whatever the input is here, you're just going to get it back. Okay. So for example, if I took just any old number, e to the natural log of 2, the answer is just going to be 2. If I took e to the natural log of 50, you're just going to get 50. Okay, and so on and so on. So that's an important property. Now, we've essentially got e to the natural log here in our QP composition, but we've got this 2 in the way as a coefficient in front of the log part. So what can we do with that? It's causing us problems. Well, there's a couple of ways to think about this. You could use a law of logarithms. Now, I'm going to do that. If you remember the laws of logarithms, this 2 as a coefficient can be moved to become a power inside the logarithm. So I've essentially got, I'll just make a partition here. We've essentially got this. So we've got e to the natural log of x subtract 3 raised to the power 2. So in other words, x subtract 3 all squared. So we're actually taking the logarithm of that. Now that's using the power law of logs. Okay. Hope that makes sense. Now then, we also need to add 1 as well, not forgetting that. And now we've written it like that, we can actually see that we have e to the natural log of something. And whenever we do that, as you can see here, whenever we take e to the natural log of something, we just get that something back, whatever it is. So my something here is x subtract 3 squared. So e to the natural log of that is just going to give me back x subtract 3 all squared. So we get from what looked like an exponential, we get actually a quadratic. So we just add 1 to that and we have our composition of functions. Okay, and we'll talk about the range in a moment. Now, if you didn't like that approach, I'll suggest an alternative for you. Alternative approach would be to consider this. So consider e to the 2x, okay? So which is what we've got in the function, e to the 2x. Now, I could rewrite that as the following. So we've essentially got e to the x. And if you know your laws of indices, of course, you just have to square it. So it's e to the x squared. And the laws of indices state that if you are raising one exponent to another, you multiply the exponent. So that would be e to the power 2x. Okay, so that's one of the laws of indices. So you can either use a law of logarithms or a law of indices with this question. Now that we've got that, if we go back to the step here, I'll just write it out again. So if we go back to this step, QP of x is equal to e to the 2, and I'll just put that natural log of x subtract 3 in a different color. Okay, so we got that step, then we add 1. We've actually got the same thing going on. So I could actually think of that as, well, it would be the same as e to the natural log of x subtract 3. Okay, but the whole thing is being squared. So I would have to square all of that and then add 1. Okay, because in this instance, my x is actually a function. So you can see here the x sitting there is replaced now by this. Okay, but it doesn't make any difference because we've just gone from the step e to the power 2 natural log of x subtract 3. So I'm fully entitled to write it like that. Now we can apply that inverse function idea again. So the idea that e and natural log are inverse, and you're just going to be returning x subtract 3 for all that. So it's just going to be x subtract 3 like that, but the whole thing is being squared, isn't it? as we've just said. So that's just going to give you exactly the same result. So it's going to be x subtract 3 all squared plus 1. And I probably didn't need the double brackets there, but you get the idea. Right, so we've got the quadratic. Now, we have to state the range. And what you can do is, of course, look at this and say, well, it's a quadratic, it's in completed squared form. The range is basically laid out for me. We know that there is a minimum at the point 3, 1. So therefore, the range must be greater than or equal to 1. Now, let's just pause for a second. I'll state that so you can say that this implies there would be a minimum at the point 3, 1, which implies that you can have all y values greater than or equal to 1. But I'll put a question mark there, or I'll put 3. Is that true? Well, no. What we need to do is go back to the idea of this composition of functions. Okay, so if we go back to that idea and go back to how the functions are composed together, we start off with this set, this domain. Okay, so we take a value from our domain, and what we do is we apply the function p to it first. So we apply the p function to it first, and we take whatever is in our domain to the range of p. Okay, so it's going from the object to the image. So we'll just make a note of that. So this is the domain of p. And this is the range of p. Like that. So you're taking some x value in here, and it's going to go to some p of x value in there. Okay, and we talked about that earlier. But if we pay close attention to the domain of p, we are only allowed x values greater than 3. Okay, so that is really important. This domain here is a set of all x values greater than 3 only. So this is really important. So x has to be greater than 3. Okay, you might have spotted the problem now. Now, once we've done the p function, we take the next step where we apply the q function. So the q function is going to take all the values from that domain to a new range, which is going to be, I'll put that there. So this is going to be the function q. And it's going to take everything from that domain. And this is where we get the q of p of x in here. Like that. So that's the composite function. So we've applied q. We've applied p first of all, then we apply q, and we get qp of x. And we know from what we said earlier that this is now going to be the range of QP. In fact, I'll write it using normal function notation. So QP of X like that. Now, you can obviously, if you do it all in one go, we can go straight from here to here, and this is the function QP. But notice the domain. X is greater than 3. So the domain of my function QP is only x value is greater than 3. So going back to our minimum, this means that the 3, which is included in this minimum, in that domain, remember it's the x value in the domain, okay, that 3 is not permitted. Okay, so this is actually not part of the domain. So it's not in the domain, this 3. Okay, but everything greater than it is. Okay, so this is wrong. Okay, so the actual real correct range would be y would be strictly greater than 1. All right, because that 3 has to be excluded. Okay, I hope that makes sense. So that basically sums up some of the subtleties of composite functions. It's quite a technical question, that one. And just to finish off this lesson, there is another activity for you to do at the bottom of the page. So I'll just clear this out and then you can have a look at it. Then there'll be some exercises for you to do. So the last activity is to find some composite functions of your own. There are right or wrong answers, of course, but there's different ways of doing it. So you've got some compositions of functions provided for you here. And your job, so things like this, your job is to find out what the original functions g of f might have been in order to generate those compositions of functions. Okay, so that concludes that. Have a go at the exercises, keep practicing, and that concludes the lesson.